Chenoli from University Malaya, and I'll be chairing this session. For the plenary session this afternoon, we are extremely delighted to have Dr. Thomas Bracegirdle from British Antarctic Survey. Dr. Tom Bracegirdle currently works as a research scientist at the British Antarctic Survey, where he leads the Polar Climate Prediction Group. He is the Chief Officer of SCAR Scientific Research Program, Near-Term Variability and Prediction of the Antarctic Climate System, which is popularly known as ANCLIME now. He is also a member of SCAR's Standing Committee on the Antarctic Treaty System, SCATS, which provides climate-related advice on Antarctic treaty papers. He has been conducting research on atmospheric dynamics and climate of the polar region since 2006. His main research interests are large-scale atmospheric circulation, climate model evaluation, and methods of quantifying and reducing uncertainty in the climate model projections. The title of Tom Bracegirdle's talk this afternoon is Winds of Change, the Past and Future of Winds over the Southern Ocean and Antarctica. His talk will be highlighting how the climate models simulate the response of near-surface westerly wind to the future scenarios of increased greenhouse gas concentration. Now, I would like to invite Dr. Thomas Bracegirdle to deliver the plenary speech.
Thank you very much for a lovely introduction, and thank you very much for inviting me to speak at this meeting. So I've been here for the whole day today, and it's been really interesting to hear the perspective of all the amazing research that's being done. So, and some of the things that I'm going to show today will link up with what's been shown earlier. And the topic of winds over Antarctica is a broad topic, so I'll just try to focus on a few key things today and some thoughts for future research as well. This is work that I've been doing with many colleagues, so I must acknowledge their contribution over the years, both at PASS and internationally. And yeah, if you have any questions at the end, of course, hopefully there'll be time to ask, and I'm hoping that what I'll present will be done in a way that can communicate across different disciplines. But if you have questions about some of the technical aspects, that's fine too. So we'll be looking at focus on two key aspects: the circumpolar westerlies that blow around Antarctica, and also changes off West Antarctica, which is a key region for broader impacts. We'll look at the past and present day changes associated with the ozone hole and tropical forcing as well, which you've heard some. And then look at future projections, so what might happen looking ahead from climate model projections. So to give a perspective on this for those who may not be familiar, a key focus of what I'll talk about today will be this belt of strong westerly winds that blows around Antarctica. And this is a picture from the annual mean near surface wind field. And you can see it's a very dominant feature. Over Antarctica itself, there's also other systems of winds. So if we look in more detail, the wind systems both near Antarctica and more widely are actually not just a constant westerly wind that blows all the time, but there's actually a combination of all sorts of mechanisms going on, and particularly over the Southern Ocean, mid-latitude weather systems are constantly circulating around Antarctica and contributing towards that westerly wind belt that you see on average. And then over the continent itself, some of the most powerful wind systems in the world exist near the coast, where you have very strong easterly winds that blow off East Antarctica. So these systems are highly important for many aspects of global circulation in the ocean. This is the strong belt of westerlies here in this schematic from Menville et al. 2018. From this perspective is strongly linked to variations in upwelling water within the Southern Ocean, and then very strong links to the whole global atmosphere-ocean system, both in terms of temperature, but also in terms of carbon uptake on longer time scales. Then in the atmosphere, we've heard this morning or this afternoon from of all the interesting research that's going on in terms of atmospheric linkages both to and from Antarctica. And in fact, it just so happens that we had this presentation shown today as well, looking at the strong connection between sea ice extent in the Indian Ocean sector and the Indian summer monsoon. So if you may have noticed that some of the linkage in terms of the sea ice impact came via interactions with the winds around Antarctica. So that's a key link in the mechanism. To give some background of why and how winds around the Southern Hemisphere do change under climate change, this picture here shows temperature change in a climate model projection with height and for different latitudes. And the height in these pressure coordinates can be converted into kilometers. So you're looking here at something between 15 or 10 to 20 kilometers in height. So this is the top of the red part is the top of where we see our main weather systems. And where you have a change in the gradient of temperature under climate change, that can affect how the winds blow. And when this happens, this can happen both at higher levels in the atmosphere and also in lower levels in the atmosphere. In the Southern Hemisphere, a lot of the main change in the temperature gradient between the tropics and lower latitudes actually occurs in these upper levels in the atmosphere, and at lower levels, so there's less of a polar amplification effect compared to what we see in the Arctic. So these upper level temperature changes are very important to Antarctic change. So when you have an increase in these temperature changes at upper levels, this acts to strengthen the westerly winds and also shift that belt of westerlies further poleward. The other effects you can see, I mentioned sea ice retreat just now. Although the effect is a little bit weaker than the Arctic, it's still important. And as sea ice retreats, it acts to weaken this temperature gradient between the poles and the equator. And this tends to weaken the jet and shift it more equatorward. So under climate change, you do have some competition between these effects on the westerlies. So if we look now at focus for a little bit in the talk on past and present day changes, and starting with something you've probably heard of, a major factor in Southern Hemisphere changes in recent decades has been the hole in the ozone layer. And this occurs above Antarctica in the atmosphere and high up in the stratosphere. And a reduction in the amount of stratospheric ozone results in a cooling at high latitudes. And this again increases the temperature gradient between the poles and lower latitudes. And so this tends to have a strong influence on surface climate and induces a strengthening and a poleward shift of the westerly winds that blow around Antarctica. And in fact, if you look at recent studies that have been looked at this in more detail, have found that there's a clear detectable impact in recent decades, particularly in the summer season. And this plot here from Banerjee et al., 2020, shows in black the ozone amount since 1980 to present day. You can see decline in ozone amount to about the year 2000, and then slight increase or early signs of recovery since then, although we have still very low levels sometimes. And if you look at indices of the westerlies, along with that, we've seen a poleward shift with that belt of westerlies, and then in consistency with the ozone amount, a smaller change since then, and a hint of a possible equatorward shift, but certainly a change there. And then an index of the westerlies called the Southern Annular Mode shows similar profile. So we can see a very clear link on these decadal timescales between ozone amount and the westerlies. Looking at the longer term contexts is important in the last few decades, and this plot here from a review paper by Vogt and Marshall shows the recent impact of the ozone hole and greenhouse gases in the longer term context. And so if you look at this starts in the year 1000, so 1,000 years ago, up to the present day. And these reconstructions come from various sources of information, including ice core data, but also other data sets from proxy data available at lower latitudes. And they certainly indicate, within these bands of uncertainty, that the recent change is certainly unusual in the context of this longer-term data set, allowing for the fact that as we go further back, there are more uncertainties in these reconstructions. And then another very important factor for climate and wind circulation changes over Antarctica is the forcing from variability in the tropics. Modes of variability relating to ENSO and other components drive circulation patterns in the atmosphere, which can be thought of as waves that connect what's happening in the tropical Pacific to variability adjacent to Antarctica in the atmosphere. So this map here shows one example of what we call standing waves or Rossby waves. And particularly, they have a big impact on this region of West Antarctica. And there are many important questions relating to this type of effect. One of the most striking aspects of these linkages is in the wind patterns adjacent to West Antarctica. So if we look at this little box here and look at the winds and how they vary over time in that box, so from 1980 through to present day, and the blue shows the variations in that box. And then the other colored lines show different components of tropical variability. And on decadal timescales, it's a remarkably strong association between the winds in that region and the tropics. And it's amazing that over such a long distance there can be such strong associations. And this is hugely important in terms of the stability of ice shelves off West Antarctica. And the more positive westerly wind anomalies induce more melting of the under the ice shelves adjacent to the glaciers in West Antarctica, and have a major role to play in how those glaciers behave. So understanding these winds, both over the Southern Ocean and regionally around Antarctica, is a crucial question in terms of how climate may change into the future. So if we look at how at future climate projections, the main tool that we have to look at these is our climate models. And a key consideration then is the performance of these climate models and how well they represent the processes that are important for these changes. And recently we've had a new data set of climate model data that's been made available in preparation for the CMIP6, the IPCC AR6 report, which has just been, at least the physical component has just been published, and the other parts are in the process of being published. And this huge new data set of climate model data was an important part of feeding into that. And one of the things that we saw that was very striking in looking at these newer climate models is actually very important improvements in the representation of the westerlies in these new models. So if you remember at the start, I showed this map of these westerly winds and mentioned that under climate change we expect them to strengthen and contract closer to the continent. Well, if we look at the position of these westerlies in the models in the present day and compare them to observations, there is a clear improvement, which is encouraging. So if this plot here shows that the new climate models in blue, and each of these crosses is a different climate model, and then the blue line here is the average of all those models. And then along this axis is the latitude of this westerly wind belt. So some of these models have this westerly wind belt too far equatorward, and other ones too far towards the pole. But in the older data set, the previous generation, this was, on average, was positioned too far towards the equator with a large spread. But in the new model data set, it's much more accurate with a less of a range across the models. So this is indicative of an improved reliability in terms of looking at these models, and does seem to have implications for projections into the future as well, which I'll show in a moment. For those of you not familiar, if we look at changes of climate into the future, it's very important to have estimates of how greenhouse gases and other forcings may change. And so this plot on the bottom left shows what we call the radiative forcing, and this is just the amount of climate change impact from of driving of climate change from different factors, and it's them all added together. So that the lines at the top here are the high emissions scenarios. So SSP 585 is the highest of those, and then much lower emission scenarios such as SSP 126. And in fact, under SSP 126, there is a weak global cooling later on in the 21st century. So there's a very strong measures to reduce greenhouse gases in that scenario. So we have a huge range of forcing scenarios. And I'll refer to SSP 585 in the middle of the road, SSP 245, and these lower emission scenarios later. If we look at the ozone hole in these projections, you can see here the rapid decline of stratospheric ozone, and then into the beginning of a recovery. In all these climate models, there's actually a recovery simulated into the future. So the impacts of this recovery are important in understanding wind changes looking to the future. So these plots here show Southern Hemisphere summer, December, January, February, and Southern Hemisphere winter. Changes in the westerly winds for different latitudes. So, and then the different colors show these different emission scenarios. And the high emission scenario, SSP 585, shows increases in the westerly winds over the Southern Ocean. But the low emission scenario, SSP 126, actually has slight weakening of the westerlies. And that's due to the fact that the recovery of stratospheric ozone in those models actually starts to dominate over the greenhouse gas signal, particularly in the summer season. And we see this in plots like this, which show that the gradual forward shift of the westerlies in the high emission scenarios, and then in the low emission scenarios, less change. But if you remember just a few slides ago, I showed that picture that had the new climate models showing improved representation of the westerlies. Well, the implication of that seems to be that now these newer models show a weaker shift in these high emission scenarios than the previous generation. So this is future shift to the westerlies, and this is more of a poleward shift, and this is more of an equatorward shift. So that in summer, the newer models actually show a little bit of an equatorward shift for low emission scenarios and a less of a poleward shift. So what we're working on now is whether this is a more reliable estimate of how things may change in the future, but certainly the improved representation in the models seems to have implications for the changes they predict. In terms of regional change, we've focused a lot on westerlies in the last few slides, but if you look more regionally, there are important changes. And here, we'll focus again on this West Antarctic region. These are maps for different seasons, but I won't dwell on this just now. I'll just jump straight ahead to the next slide. And what this one is showing is seasonal changes in the westerly wind component over the Amundsen Sea embayment in different seasons, and you can see slight increases in the westerlies over that box in climate change scenarios into the future. The main point here is that this dashed line follows the solid line quite closely right towards the end of the century. And the dashed line is the so-called model uncertainty. So how is the measure of confidence of this prediction across many different climate models? And it's very large, so that even though we have quite a large increase in the westerlies over the Amundsen Sea embayment, there's also not much agreement between the models. And it turns out that a large part of this seems to come from how well they represent that teleconnection, that connection from the equator to the pole. So this plot here, don't worry too much about the detail, but it's a measure of the source of that wave pattern that I showed earlier on, the pattern of waves from the tropics to the poles. There are triggers for that. We call them Rossby wave sources, but you can just think of it as a trigger of these waves. And climate models show a change in this trigger in the West Pacific subtropical region. Okay, this is just an average from many climate models. And if we look at the full atmospheric circulation change across some example models, this is 4 different climate models here, and the atmospheric weather patterns that they predict for the future, there's a huge range. And if the cross here is over West Antarctica, near that box, and you can see there that the different weather patterns there are consistent with that large uncertainty in the westerly wind projection off West Antarctica. But if we, so this line here is just the full climate model projection as it appears in the climate model. If we isolate that tropically forced bit, the part that's linked to that wave pattern to the tropics, what you see is that captures quite a lot of that difference between the different climate models, seems to come from that component that's that tropically forced component. So the take-home message from this slide is that the uncertainty in how the westerlies will change over West Antarctica depends critically on how well climate models represent that linkage to between high and low latitudes. And presumably the same is true the other direction as well. So to summarize, near surface winds over Antarctica and the Southern Ocean have changed significantly in recent years and decades. Some changes can be clearly explained, and others still have large uncertainties in terms of explanations. Future projections exhibit a strong dependence on the forcing scenario. So we have a clear poleward shift and strengthening under high emission scenarios of the westerlies, but weaker shifts in the latest generation of climate models. But there's a large uncertainty over the regional and coastal change around Antarctica, which seems linked to how well the models represent that wave connection between the tropics and Antarctica. So there are a number of challenges for future research. So the large uncertainty in modelling past and future regional Antarctic circulation will require improved representation, as I've just mentioned. Little is known about the near-term annual to decadal predictability of Antarctic circulation. So not just the end of the century, but what's going to happen in the next year to decade. And then for future projections, the relative importance of stratospheric ozone recovery and greenhouse gas forcing remains a major topic for further research. And it will be very important to work together as an international community to collaborate on the major scientific challenges, and in particular through programs run by the Scientific Committee on Antarctic Research and other linkages, I think are going to be really important to tackle these big problems. And agreements like the MAU that was signed earlier today, I think, are really excellent ways of working together. And with that, I will end. Thank you very much for listening, and I look forward to any questions you may have. Thank you very much.
Thank you very much for the very interesting and informative talk. on the changes of southern hemispheric surface wind in the future. So I'm sure that we all have many questions to ask, but with the limited time, let me invite just maybe 2 burning questions for Dr. Bracegirdle.
Yes, sorry. Can I ask, Sheeba?
Yes, yes.
One of the issue raised in CIMIC 6 and also the other model is the fact that they cannot model ENSO properly. And basically, I think there's some work that I think we have done ourselves in the sense that the shift of the Hadley cell will shift where the Rossby pattern, during ENSO and also during La Nina. So in that sense, how does that contribute to the still uncertainty of the CIMIC in terms of the tropical forcing that the CIMIC is trying to simulate?
It's a very good question. Yes, it does contribute a lot. So that there was, so in the differences in the models that I showed in the patterns of, in the isolated tropical component, some of that was from the different ways they simulate the westerlies through which the waves propagate, but a lot of it was also uncertainty in the Rossby wave source change across different models as well. And that was linked both to differences in the Hadley circulation expansion, but also the how much the Walker circulation weakening of the Walker circulation. So both mattered, the uncertainty in the Rossby wave source and the propagation between the different models. Yeah, so Matt's paper has more information on that. Yeah.
Thanks, Dr. Thomas. Any more questions? Just one more question. If not, thanks once again, Dr. Thomas Bracegirdle. So with this, we have come to the end of this session today. On behalf of the organizer, I would like to thank the plenary speaker as well as the participant for joining us today. So we will meet again tomorrow at 9 a.m. Malaysian time for the policy and governance plenary session. On that note, I wish everyone good health, stay safe, and have a good evening. Thank you very much.